Can you hear me? At the back? Hello, at the back? Can you hear this okay? At the back? Thank you. Welcome. This is first lecture, term 2, machine learning, COMP9417. So what I'd like to do in this first lecture is talk through regression, and we have 2 weeks to talk through regression. Today I'm going to just introduce some aspects of regression, but I'm also trying to do another thing. I'm trying to introduce some general and very powerful ideas about machine learning. And hopefully I can convince you just by working through linear regression, very, very simple approach, been around for more than 100 years, that these are important issues, and moreover, we can solve them in quite a standard way. And later in the course, I'm going to try and convince you even that these ideas generalize right up to the very powerful and large AI systems that everyone is using today. So that's the objective. We'll see at the end. You can tell me if you're convinced or there's still some things that you would like to consider. But before I do that, I just want to do some housekeeping. Now, unfortunately, I can't, for some reason, display on my laptop what I wanted to show you. But what I want you to do, if you haven't already, is, so we're going to use Moodle for basically everything this term, except for Teams. The idea is to try and cut down on communication channels, right? So we do have a course email, but please reserve that for important and probably private communication. Everything else, question-wise, please go through the forum. So if you've looked at Moodle, you can see that there's actually at the top, or just after getting started, at the top, there's a section for forums and chats. So for all sort of questions about, you know, why is that idiot not uploaded the lecture slides yet, go to the forums, ask there. Some of the course staff will be monitoring. Sometimes me, more usually Omar, our amazing course admin, will be monitoring those. There are several reasons for this. One is we just want to cut down the number of communication channels, as I said. Also, many questions that you have, other students will have as well. So if you ask the question and it gets answered, and hopefully we do answer it in a timely fashion, anyone else who's got the same question or approximately the same question will see the answer. And that hopefully will reduce the communication bottleneck. Right, so having said that everything's on Moodle, if you go on down the Moodle page, you'll see some information about the lectures. You must all have seen that or looked at the timetable because you're here, but for those on the recording, the lecture times and locations are there. So the lectures are every week, apart from Flexi Week, week 6. So we go 1 to 5, and then we go 7 to 10. However, tutorials don't begin until week 2, so next week. So there's no tutorials this week. And the reason we do that, it's not perfect, I admit, but the reason we do that is we try and make the tutorials dependent on the lecture material in the previous week. Okay, so most weeks with tutorials, we've got, you've all got a tutorial hour, and we're going to give you some sort of tutorial style questions and some practical work to go through. Right, now, I strongly recommend that you try and make the most of this. Okay? So I'll talk about the assessment structure in a moment, but if you ask me, how do I pass this course? My answer is every week, try and do as much as possible of the tute questions and the lab exercises. Go through it preferably by yourself, right? Preferably by yourself. And, you know, of course you can, you know, ask friends and work together and all that kind of stuff, but try and solve it first by yourself. I strongly recommend that as really the quickest and deepest way to learn this kind of stuff. It may look hard in places, but actually, if you keep at it, if you keep going, you'll start to see and it'll make sense. And then having tried it for yourself, go to the tute and ask the tutor. We've got fantastic tutors. Many of them already have their PhDs. They're very experienced, they're very friendly. They are a great resource for you. So please, please, please make use of them. They're great people and they're going to help you. They're there to help you. Now, the reason I say that my answer to the question, how do I pass this course? Well, obviously I'd like to see you at lectures, or you can watch the recordings, but you need to kind of go through this by yourself. I mean, you can look at the stuff I'm talking about here, and I do try and work through some things to give you an idea, but basically you have to, you know, basically do it yourself, because out there, once you finish this course, and whether you go on and do research or have a job, you know, ultimately you're the people who other people will look to. You're the machine learning person, right? Tell me how to solve this problem. And if you try and do it yourself, that's the best way to get to that level of ability. And the third reason, I'm not sure if I'm counting reasons, but anyway, the final reason is that the final exam in this course is an invigilated in-person exam. So we use Inspera. If you haven't used Inspera before, it's simply you go to the exam room with your own device. Inspera locks down your device. You start the exam. You're there in the room for 2 hours, and you have to basically solve the kinds of questions that we've been giving you every week in these tutes and labs, right? So the best way to prep for that is to actually do the week-by-week stuff. So hopefully that makes sense. And I should mention, this year, every iteration of 9417 we've put a hurdle requirement in place. So you need to get obviously try and do as much as you can on the assessment, and that will help your marks. I'll talk about that in a second. But you do need to be aware that there's a 40% hurdle. So in other words, you need to get 40% on the exam, irrespective of all of your other assessment marks, to pass the course. So last but not least, on the sort of admin stuff, the assessments are kind of in the same vein, right? So we have a sort of common way of thinking about how to do the work on this course. And the way to think about the assessments, there are 3 of them. We just call them homework 1, 2, and 3. One of them is, for admin reasons, called a project, but in this iteration, it's not a group project. It's done individually. If you look at the course outline, you will see that. But they're all in the same vein, right? So they all try and take the ideas in lectures, tutorials, and labs and just push it a bit in various directions, right? So there's some theory stuff, there's some problem solving, and then there's some programming, right? So we're trying to cover all of those 3 bases every week, and those homework assessments just take that and extend it. So just to repeat, we have, if you look at the course outline, we have 3 homeworks. Homeworks 1 and 2 are, okay, I better get this right. Yes, they're 15% each, And then we have a slightly longer one called Homework 3. Again, due to admin reasons, that's termed a project. That's because sometimes other iterations of this course want you to do a group project. We've decided not to do a group project for various reasons. Ask me later if you're wondering. But that's worth 20%. So homework 1 and 2, 15% each, so 30% in total, and homework 3, 20%. And the aim is to finish that homework. I think week 8 is the submission. We might have to extend that depending how long it takes to mark some of this stuff, but the idea is for you to get all of your assessment done and have good amount of time to prep for the exam. And of course the exam is the remaining 50%. I think I covered everything I wanted to on the admin side, but has anyone here got any quick questions on admin stuff? Nothing at all? I must have forgotten to say something. Okay, good. All right, well, without further ado, let's get into it. Okay, so oh yeah, one thing I didn't say is that I noticed just yesterday, in fact, that I'd forgotten to, or omitted to add some of the references. In the lecture slides, I have these references for each lecture. They're mostly common to each lecture slide. So these are the course books. And you'll see I've put URLs. At the end, sometimes I cite particular references that I use at various points in these slides. So I'm going to also put the ones specific to that lecture in citations at the end. I think there's only 2. Now, I just want to note, all of these are free. Well, actually, no, they're not all free, but sorry. Yeah, I think the O'Reilly one is not free. But this one we lean on quite a lot. This first one here, Mathematics for Machine Learning. I sometimes just call this the MML book. It's a great book. Does have some ordering differences from the way we look at things in this course, but it's a great resource and it's entirely free. The PDF is entirely free. The second book, which we do refer to, again, it has a different structure, but we dip into it from time to time. So if I talk about the elements of statistical learning, that's the book. There's also another more introductory version of this, which I cite at the end. I'll also put a URL there. They're both free books. The second one, I'm giving a reference to at the end of these slides. It has both PDF, it's a free PDF as well, but there are 2 versions. One where all of the practical material is in R. So if you're an R fan or you're very experienced in R, you might want to go with that. The other one, which is probably more for most people in this course, has all of the practical stuff in Python. So you can go through the exercises in there. This third book we don't refer to that much, but if you're into probabilistic modeling, this is an earlier version, but has more of the core things that we've got. You can also look at the later version. You might want to do that because he's changed the practical stuff. There's now 2 volumes, which is a little annoying, but it's become very big. But in the second edition, if you think this is interesting, go and look at the second edition because all of the practical stuff has also migrated to Python from MATLAB. Peter Flack's book is sort of standard now. Not very new, but everything that is in it is solid and has not changed. Unfortunately, I don't think he's made a free PDF available yet. David Barber's book. If you're coming from stats, you might like this. Again, it's a bit of an older book, but it's full of solid statistical stuff. And again, there's a free PDF. This last one is a little bit out of date, but it has some nice sort of, if you're coming from the sort of engineering side, like ML ops kind of stuff, you might get into this. I would say that there's probably now more recent books that kind of supersede it, but it's still got some good stuff in it. So I will refer to other things going through, but if you're wondering where the course resources, go to the lecture slides and follow the links. I will, of course, try and add those as well to the course outline. So in this lecture, what we're trying to do is two things. We're going to say the problem that we need to address is given a bunch of variables or features or attributes which are numeric, we're trying to predict a number. We're trying to learn a model to predict a number. So I'm calling this here numeric prediction, and it's also a supervised learning task. So what we need to do is figure out, well, what is the general framework into which that fits, and how to solve it. Now, the general framework is going to be, hopefully, the way that you glue together everything that you see in this course. But for regression itself, there are particular things. One is the well-known least squares error criterion. Then later, you might be worried about this linearity, because that's quite a strong constraint. So I'll talk a bit about non-linearity, and we're going to revisit that as we go through the course. And then next week, we'll talk about gradient descent, which again is something that you will see all over machine learning. And it actually is quite nice to go from the approach that we take today and Friday and look at how that generalizes to gradient descent. Okay, so here's the general setting. Well, I say general setting. You'll read different sources on machine learning, and they will have different sort of versions of this general setting. But here's the one that I think makes most sense, is easy to remember, and applies to, I think, pretty much everything that we cover in this course. So I'm saying the machine learning problem, or the framework for machine learning, is given a problem to solve with data, and we might talk a bit about what that means. Step one, select a class of models and a loss function. Class of models and a loss function. Then, step two, fit a model to a training data set to minimize the loss. So use that loss function, use the data, fit the model to the training set to minimize the loss. And then step three is use the model to predict for data not in the training set. Now, some of you might be coming to this course having had a background in stats, which is great. Sometimes people wonder, what's the difference between stats and machine learning? Well, it's not an easy question to answer. And over time, they've started to become quite similar to each other. You might say, well, stats is a more mathematical approach and machine learning is a more engineering approach. And that's sort of true, but many stats people now get heavily involved in engineering, and many machine learning people get heavily involved in the sort of statistical mathematics, particularly on the research side. My personal answer to that is the difference between stats and machine learning is that machine learning comes from a tradition in AI, artificial intelligence. And the tradition there is all about autonomy. And classical AI, usually people think about autonomous systems like robots, like actual physical autonomous systems. These days, though, we have the same kind of idea, but purely in software. And again, the classical name for that in AI is agents. So agents, the whole point is to relieve us humans of work that either we can't do, we don't know how to do, we won't do, we can't afford to do, all of that kind of stuff. So really, I think the difference between stats and machine learning is that machine learning is ultimately designed or oriented towards autonomy. That's really the idea. So this step 3 becomes really critical. It becomes that the key point of machine learning with an autonomous system is to be able to handle in a reasonable way stuff that it hasn't seen before being let loose on its autonomous path. Right? So if it's actually a software agent, like right now you can go and buy a subscription to an AI company and they'll tell you how to set up agents using their system. What's the key problem with that? Well, the key problem, there are usually several key problems, but a critical key problem is autonomy. Right? To what extent do you believe the agent truly is autonomous, and more importantly, autonomous within the guidelines that you set out. So you want it to be able to do the things that you want it to do and not to be able to do the things that you don't want it to do. And that's actually still a really hard problem. And the reason for that is really number 3. Right? The reason for that is that if you train a model, great, okay, does really well on the data, but you actually then want it to be an agent or be autonomous, and then how is it going to do? How well is it going to do? It's number 3 that's the key, really the ultimate key. Because if you could have very strong guarantees, you know, the world would be just amazingly open to applications. The thing that holds everything back, or we need to be cautious about, is this number 3. And the one word term for number 3 is generalization. Right? It's generalization. You want to go beyond what you've been told in the data, which mostly you assume is good data and it's correct. So doing well on that data is kind of like known. Right? You know, here's the data, this is what happened. Okay, my model should mimic that and you know, as accurately as possible, unless I believe there is something wrong with the data, and I'll you know, I don't want to be too close to that data. The key thing is number 3, is generalization. Okay, so let's assume we have, in the general setting, that sort of background, that's the sort of framework. There is a bunch of theory in machine learning called statistical learning theory. Ironic, because I've just been trying to say that statistics and machine learning are not the same. Statisticians may quibble with the fact that, is this really statistical learning theory? It didn't originate with that name, but it's come to be known by that name. And the kind of still the most commonly used version of that is a set of theory actually developed by a statistician called risk minimization. And there are various forms of this. The one I want to draw to your attention here is empirical risk minimization, or the ERM framework. Okay, so there are other approaches, but to try and capture in one slide a sort of theoretical framework for machine learning, I'm going to use this one. So we have a class of functions. Now, this covers many, many kinds of machine learning, but mostly people are thinking of a couple of simple types of functions. So they're either, so the class of functions is y. So I'm drawing y in bold. to indicate that it could be a bunch of things. It's not just like a scalar value. In general, it could be some, it could be a vector, could even be a matrix, could even be a tensor, which is just a multi-dimensional matrix, more than 2D. And the same for X, right? So I'm kind of not specifying what they are, but I'm just saying there's a thing, it's called Y. It could be quite complicated. Like it could be something you want to, it could be a single number, but it could be something like an image that you want to output, or whatever, a time series, whatever. And then there's an input, and then there's some parameters theta. The input is X, the parameters are theta. And Y should be a function of those things. There are even more general frameworks where you don't actually necessarily have to have a function, or it could be a non-deterministic function. But let's just say it's, familiar function, something you would code up in Python, right? Let's use that to make it concrete. Okay, so input data and parameters. And we also need, in this framework, a loss function. Now, the whole point of the word empirical is that we want to minimize risk, or whatever the loss function tells us is that risk. So the risk of making a loss, if you want to think about it in those terms, or just error. And then you want to, given the actual data that you've been told, Y, and you've been given a bunch of that, hopefully enough, to make a good approximation of this function. And once you've learned the function, you will use that function of X and theta, or parameterized by theta, to make a prediction, and that prediction will be Y hat. So we use the little hat to indicate that this is coming from the model, not the true function. The true function is not known, right? So Y is this thing that's unknown. We might know some of it. In fact, I should correct that. So we assume that some of the values of Y are known. But as I said just before, the key point is to go beyond what we know and do prediction. And the empirical risk is usually something like an average of the loss Y to Y hat that we have data on. That's why it's empirical. There are other forms in this framework of risk. We won't get into that now. We'll come back to this at various points in the course, and in week 10 we'll spend a bit more time developing this framework. But the empirical risk is just when you have data from this hidden function, what is the loss of a particular thing that you've learned, right? So you learn something given some X, and you learn the theta. And the idea of ERM, or the idea I'd like to communicate to you, the key idea with respect to what I was saying before, is that ERM says, or the theory says, if we do well on the training data, then given various assumptions that are built into the theory that I'm skipping over, then we will do well on for generalization. We will be able to generalize well beyond the training data. Okay, so if you minimize empirical risk with all the caveats in the theory that I'm skipping over here, then you will do well on data that you haven't seen. Now, actually, the constraints that I'm skipping over are quite strong constraints. Quite strong. So one of them that you may have heard of is the sort of distributional assumption. Now, we're not making any assumption about the form of the distribution. That's why this kind of framework, or part of this framework, is sometimes called distribution-free learning. But we are saying that to do well in this generalization sense, according to the ERM, you'll do well if the data that you see, that you have to generalize to operate in the world as some autonomous system, is from the same distribution as the data that you saw in training. Okay? So you're not saying it's a normal distribution or anything about the kind of distribution. You're just saying it has this same distribution property. All right? So there are other constraints in the setup, but that's I guess the key one. Okay, so I want to just highlight what I said, if I can get this thing to work. Let's see. Okay, so this is my cartoon version of these two sort of sides of the machine learning coin, as it were. So what I'm trying to do here is illustrate, well, I call them roles. I don't think that's a great word, but what I'm trying to get across here is the idea of learning or training, which I guess is this thing here. This is training. And this is, using, applying, or predicting. Right, so this is estimating parameters by doing training. So I've put in this little box here something like a machine learning program. And the program could be called, train regression. Now, I'm going to say in a minute that regression is actually overloaded. So what it means here is train a regression model. So the data is of this form. The input is pairs. I'll just assume this is what's called simple linear regression. So there's one input and one output, and they're all scalar values. And you probably can't see this, but there are n of them. Doesn't matter, we'll see this again. And the form of the regression, the class of models is this. Okay, over here we can see it. It's going to make a prediction based on a single parameter b. Okay, so we called the parameters theta. In this case, there's only one. It's just a single number. It's actually the slope of the regression line. We're assuming that the regression line goes through the origin, so there's not even offset parameter. So the question is, what is the algorithm? What is the algorithm that goes through that the training program executes? Goes through the data and somehow comes up with something. And that's what we're going to derive in the second hour of this lecture. Okay, so that's training. Now, I've called it here estimate parameters. And for the first 3 weeks of this course, that's actually what exactly the algorithm will do. It's told, here's the model class, here are the little slots, you can think of them as variables, where you put parameter values, and the job is to find the best parameters, essentially the ones that minimize the loss function. Not all algorithms are exactly like that, and then we'll extend this idea of parameters, but it'll seem quite natural when we do that. So parameters is, again, overloaded. It's either actual parameters or just things that need to be learned by the learning algorithm. So I put question mark here because we haven't said what the learning algorithm should be. And for regression, there are several algorithms we could use. For other model classes, there are certainly other algorithms. But that's the general scheme for training, right? It's executing a program to produce a model. Some of the model is built in or specified to the program. Some of it is variable, and those variables need to have values attached, and those are the parameters. And once you've done that, I've called this apply the parameters, or we can think of it as predicting. Okay, so This is the setting I mentioned before that is kind of like the AI version. So machine learning is ultimately thought to be, you don't have to think of it as in this, you could just say, well, I just want to find the model, that's fine. But in machine learning, why is machine learning even needed? Because we got statistics already. Well, basically because people want to solve problems for things like robots or, you know, high school students' homework or, you know, whatever it might be. The prediction task takes the model and for a particular input, which should be like one of the inputs it's seen in the training set, this has the same form, it's going to estimate an output. So it has the parameter that was learned from here. Right? The output of learning is essentially the set of parameters, only one in this case. And it knows the model form, and here's the input, and it says, okay, here's your output. Right? So it could just be, this could actually be the code, or in Python you might, you might want to write it out to tell the user or apply it to a bunch of data or whatever you might want to do. But this is the actual code that's used. So the job of the learning, as I said, is to find something that will fit in this model that you can then use to predict. All right, any quick questions about that? That's a sort of very high-level overview of the whole of machine learning on this course. Yeah?
Are we assuming that the process is stable, so like the data?
Yes. Great question. I'll just repeat the question for those watching the recording. So the question was, are we assuming that the underlying function f from where the data is sampled is stable? And the answer is yes, we are. And that may not be a correct assumption, but we'll make that assumption to get started. Okay, we'll assume that, and this is actually part of the ERM as well. Maybe I'll just flick back to that before we pause. So, okay. So as I said, this is like a really simple version. If you're from stats, you'll say this is not a regression equation because it's it's missing an error term and things like that. And in fact, the version we're going to derive has two parameters. But here we've just got a scalar value y, a scalar value for x, scalar value for y, and a scalar value for b. So just a number. And it just models the y as a function of the output. So you plug in, so b is fixed as we said, you plug in x and you get y. And to train it, we need that data. So actually there's a bunch of stuff. I want to go fairly quickly, but it should all be fairly self-explanatory. So regression, the term, so now we're talking about regression. So the regression, the term is it's overloaded, has context-dependent meanings, can refer to learning, or it can refer to the equation, the model itself. So both of those left-hand and right-hand side things. Now here's a very, very simple cartoon version. You've all seen this kind of stuff way back. So we have inputs and outputs. We assume y is the output. I'm using this terminology instead of statistical terminology because I want you to focus on the fact that we're learning a program, right? We're dealing in code. So we have to estimate b, given the data, estimate b or b hat. Sorry, I'm talking to the wrong thing. I'll just say all that again. Here's a very simple situation. We've got data, the red dots. I haven't labeled the axes, but x is the input and y is the output. And the regression equation is going to be the black line. So b is just going to be the slope. It goes through the origin, so we don't care about the second term, which we will derive later. And it's just a very simple input-output function. So the two setups that we had, training and then prediction, they both come, they're both obviously fitting fitting this, this setup. So why is this even useful? So we are going to derive equations for linear regression in literally an input and an output, okay? So at the beginning of the introduction to statistical learning with Python or R, they have this example. So you can go to that section in the book, and they show this data set. And it literally is a single variable and a single variable input and a single variable output. So it's univariate regression. Univariate just means single variable input. And here the prediction problem is sales. And so the task or the problem is learn a model, a regression equation, as a function of TV advertising budgets for 200 different markets. So the red dots, there's 200, I assume there's 200. There's 200 of them, and the input is the TV advertising budget on the x-axis, and that's in thousands of dollars. Yeah, okay, so this is, I guess, from a while ago, but the maximum seems to be 300,000. And then on the y-axis, the thing that you would like to be able to predict is the unit, thousands, the number of units sold, so thousands of units, sales in thousands of units. And then the regression model is that blue line. And you can see now actually it doesn't go through the origin. And so we would have to model this with two parameters, which we'll get to shortly. So the slope of the line, B, and then we have an intercept parameter, A. But this is nice because it's kind of reasonable, right? It's a reasonable question that some advertising person might ask. Oh, or some company might ask, the advertising people. Oh, we're spending this much money on advertising. What do you think our sales are going to look like? Right, so obviously there's a bunch of things that we're not told here, like time period. This is like a static snapshot it would have to be, or some historical data over a fixed period of time. Is the future like the past? You know, you have to make that decision. Are we assuming that the data that we've trained on, historical data, will be in the same, that the future will have the same sort of distribution? Maybe it will, maybe it won't. That was the assumption, remember, to do good generalization. But we can certainly imagine modeling it with regression, which is nice because even, you know, you might be thinking this is just too simple a model, but actually it could be useful. Okay, so this kind of summarizes what I said, and the data is going to be these XY pairs. We'll assume there's n of them. And if, in fact, the relationship is linear, well, actually, let's just do a quick sense check. Do we think the relationship is well modeled by this linear model? Yeah? It could be, yeah, great answer. Yeah, okay, great answer. So it could be, but it's very, there's a lot of movement, if you like, or I'm trying not to use the word variance. There's a lot of difference between, on average, the red dots and the line. And furthermore, you might think that that difference changes over the model. So if you look at the left-hand end, it doesn't look very linear. And over towards the right-hand end, you're not sure if the sort of variation is increasing or not. I mean, it could be, who knows. So you might look at this and say, well, okay, you're telling me that this is a linear model, but maybe it's not the best model. And you know, that's totally acceptable, right? But you might say to a first approximation, it's kind of linear, right? So it's a useful thing to do, or it can be. All right, so that's what we're saying here. If you believe that there's a linear relationship, then simple linear regression should be a sufficient model. Now, there's another thing I want to stress here. There's a bunch of stuff that goes on outside the machine learning that you have to somehow manage. And here we're saying, yeah, it could be linear. Let's try a linear model. That's not machine learning, that's kind of the practitioners around that, right? And when you go into the real world and do this kind of stuff, you'll find a lot of that, right? However, one reason we start with regression is that it's very often a useful thing to try. Maybe not a univariate linear regression. We'll see multivariate regression next time. But positing a linear model, if the data really is pretty much linear, then you're done. So you've saved a lot of time and probably money. If it doesn't work that well, then you know you've got to do more work, spend more money, use a more powerful model class, all of that kind of stuff. So pragmatically speaking, it's a good starting point. Now, on the error, we have, right, so just go back. So again, if we look at this, we see this often the points, the red points are quite a distance from the blue line. So the loss function we're going to use is based on that idea. So we've got an actual value for every point, yi, and then we've got a prediction, y hat I, which is this model a plus bxi. So for every xi value here, the corresponding prediction is, well, actually here's a point that's dead on. That's purely by chance. But over here, the corresponding prediction is here. Hopefully you can see that on the recording as well. But the actual value is not, it's below. And then here, the prediction is on the blue line, but the actual value is way above, right? It's about 20,000 sales above, right? So not an inconsiderable amount of error. So we can call a term that's used for that. I said error, but it could also be referred to as a residual. It's just the difference between the actual and the predicted value of the model, the actual value and the predicted value. And then we have this idea of squaring those residuals and summing them all together. And so some terminology you'll see in various places is just the name for that sum, which is the residual sum of squares. And that will be the basis of the loss function. Sum of squared errors, we're actually going to use a variant of that where we take the mean of that and then derive our equations. Okay, let's see. I'm going to go quite quickly through this, but because some of you have seen correlation before, and correlation is a sort of obvious thing to think about, and it does actually kind of relate to regression. I'm going to just take a quick digression into correlation and covariance. So the correlation coefficient, probably most of you are familiar with it. It's a number between +1, -1, and it's designed to measure the degree of association between a pair of variables, let's call them x and y, but also how much scatter there is in the data, right? So essentially, it's a linear relationship that's being posited, and you get a scalar value between -1 and +1 that will tell you these two things. Okay, so if in the data, if we have high values of x at the same time as we have high values of y. So we're thinking xy pairs, right? They have to line up in rows. And at the same time, when x is low, y is low. And the scatter, which I'm not going to define, is low, then there will be a reasonable value for that correlation coefficient. Again, I'm sort of hand-waving deliberately because I don't really have time to get into the details. On the other hand, if there isn't really a particular association and there's a lot of scatter, then the correlation coefficient is going to be close to 0, right? Now, the sort of classic version of correlation, there are many, many correlation coefficients. This is only just the sort of entry-level version. Pearson's correlation coefficient, sometimes called, and this I'm not even defining it properly. It does assume, again, a linear association. Okay, and as I said, Pearson's correlation coefficient is defined in terms of two things: the covariance and the variance, or the standard deviation of the individual variables. Okay, so what are these terms? Well, the variances are, classically, take the mean of the x, which is our first variable, and then for each pair of data, for each element x in all of the pairs of data, subtract that from the mean, square it, and then basically take the average. Does anyone know why we do a 1 over n minus 1 instead of a 1 over n, which would be the arithmetic mean? Any stats people in the room? Yeah. That's the version I usually go to. Yeah, that's right. Yeah. It's the degrees of freedom, yeah. So the simple version, which is my preferred understanding, is that there are n minus 1 degrees of freedom here for n data points. It's out with the scope of what we're doing here, but if you're curious, it's a correction that is mainly important if you only have a small data set. And sometimes you only have a small data set, like maybe 10 or 20 points. So for modern machine learning, that's really not an issue, because the difference between dividing by n minus 1 and n for very large data is really not a big deal. But anyway, that is the sample variance of both x and y. So the key thing I want to draw to your attention is just taking the difference between the mean, because that's going to be a key thing in when we derive regression. And very importantly, correlation looks at the sample covariance. So what is that? Well, it says for each pair, remember each row in your data table, find the mean of each column and then take the difference. You can compute it in different ways, but that's what it means. And again, take the average of that. And if you look at the formula, it's really all about the covariance, right? And the covariance is that thing we just said. When x is high and y is high together, or they're low together, and the bit about the scatter is captured by this stuff here, right? Because you're dividing by that. So if scatter is very high, that goes in the denominator, and that will reduce the impact of covariance, which could be quite high, on the correlation coefficient. So if you're doing correlation, just remember these two things are going on. You're looking at the degree of association, right? And covariance. There's a famous saying, does anyone know what it is about correlation? Yes? No, you go. Say again? Yeah, correlation does not equal or does not imply causation. And you can see that here, right? There's nothing to say that x causes y or y causes x. It's just, do they go up together, do they go down together? There could be a third variable, z, or z if you like, which is controlling x and y going up and down. And that would be causal, right? But you don't even have the data on that. So correlation is this very nice but very simple idea about relationships. But it does have it does have some of the key components that we use in correlation, in regression. And this idea of covariance is actually extremely important for a lot of algorithms. So we're not going to dwell on it too much, but covariance is this idea of going up together, going down together. And here we can just think about it qualitatively in terms of the relation of each value compared to the mean. Right, so if they go up together and go down together, that's going to be a positive correlation. If one goes up and the other one goes down, and vice versa, then it's going to be a negative correlation. So you get correlation in both directions, which is nice. But of course, if there is no association like that, and also if there's a lot of scatter, then it'll be close to zero. So a practical use of correlation is checking to see whether there might be some linear association, particularly looking at, essentially looking at the covariance. And as we said, correlation does not imply causation. All right, hopefully I've got enough time to do this. So let's look at univariate linear regression, just of the form that we had in that problem of predicting sales from advertising spend. I'll introduce it via another example. This is from Peter Flack's book. Suppose we want to investigate the relationship between people's height and excuse me, people's height and their weight. And in particular, can we determine a relationship between if we know their height, can we determine what their weight might be, or predict what their weight might be? So setup is get n measurements, xy pairs, h, wi. So wi is the thing that we're trying to predict. H is the thing that we will always be able to measure, presumably. And then a univariate linear model, linear regression, is going to assume a linear equation that says W is equal to, or is a function of, A plus BH. So the function, the linear function is A plus BH. So W equals F of H and the two parameters A and B. And the parameters A and B in this case such that are going to be chosen to minimize the sum of squared residuals. Okay, so I'm just going to show you the result, and then we're actually going to do the general derivation. So someone was asking me before about the math required for this course. So basically, we need a bit of calculus, we need a bit of linear algebra, and a bit of probability / statistics. So here is, I guess, the calculus bit. So what is the loss function? Well, it's this residual sum of squares. I think he's using RSS here. I'm going to use mean squared error, but it's essentially the same thing. And how do you find a minimizer or a maximizer with calculus? Someone who hasn't answered before. Huh? Yep, we're doing optimization, we're doing calculus. How do we find the optimum? Partial derivatives equals 0, and what is that doing? Well, okay, hang on. You've missed a step. That is actually what we're going to do. But we're optimizing. What are we optimizing on? Sorry. Okay, we'll do this in a second. We are optimizing on a function of A and B. The loss function. Yeah. The loss function. Does it make sense? So it's kind of like another layer. There's two sort of functions going on. We're trying to learn a regression function. What is the choice of regression function? In other words, what is the choice of A and B? Remember the training thing? We just found B. Oh, here we got A and B, but it's the same problem, right? That's the learning thing. So what we didn't discuss in that little setup was how do you find a particular B? I just put a question mark there. So one way to find A and B is to say, well, we want to do an optimization. And the optimization is going to be based on minimizing a minimization of the error, the sum of squared errors, or the mean of the sum of squared mean of the squared errors. Okay, so for that particular example, if you were to do this, you would need to do find the partial derivatives. So we have two parameters, A and B. So we need to differentiate. Well, what do we need to take the differentiation of? Sorry? Yeah, but why? What is it that derivatives are? What is it we're optimizing? Well, we said it's a loss function. Loss function is of A and B. So we take the partial derivatives of the loss function. And how do we compute the value of the loss function for particular A and B? It's on the slide, but I just want to make sure that everyone's seeing it. Well, how do we make the prediction? We already know in the training data we've got value of y, or in this case the weight, w. But how do we make the prediction? Yeah. Our prediction, yeah, exactly. And we take the difference and square it, exactly, right? So we take the, we actually do the prediction, right? So, okay. Well, all right. So we imagine that we're doing the prediction. We don't actually have to do the prediction, as you'll see. Okay, what else do I want to say about this? Okay, I want to point out just that when we've got the result, I'm not going to step through it, but yeah. So as you said, it's we need to take partial derivatives with respect to A and then also with respect to B, because we need to solve for both. Set to 0. Okay, so we're going to get an expression for A, or A hat correctly. Notice that we've got this in terms of means, W, and so this bar W is going to be the mean notation that we use, the average arithmetic mean. And that, that expression is in terms of B hat and the mean of H. And then B itself, B hat rather, is an expression in terms of, and if you look at this, you kind of see the relation to the correlation that we talked about before. Because in the numerator, we have something that looks pretty close to our covariance. Okay, so hopefully I can get through the derivation. So let's see. Okay, so we need that. Okay, so as I said, if this goes disastrously wrong, I apologize. Okay, so we want to, I'll try and go quite quickly. I won't do all the steps, and I might not get finished, but I'll finish it off next time if I don't. So in the example of height and weight, we're trying to fit something like this. We want to have a regression model y. So I've switched now from height and weight to the more standard. So x is height and y is weight. So if this is the model that we want, this is the kind of thing that we want. We need to ask the question, which function, this is a function, linear function, which linear function? Now we've sort of implied that you could take the residuals, sum them up. But there's, and minimize that, which minimizes the distance from the line to each of the points, which is correct. That's intuitively what these loss functions are doing. But how do we implement this? How do we sort of make this algorithmic, or I guess statistical algorithmic? So you're all familiar with the sort of squared function. Right, so this is x, y, so it looks something like this. Okay, so the minimum is not supposed to be 0. So if we're trying to optimize, so minimization is a form of optimization. So optimization, I'll talk more about this next week. We want optimization of the loss function to find the best model. So if this was, let's say f of x was x squared, this function here, right, this thing here, how would we minimize it? Well, there are different ways to do it, but the most prevalent one is to take the derivative, which I'll denote by f prime of x, and set it to 0. Okay? So the x that makes this minimal is the minimizer. The minimizer. And we'll put a hat on this because we're now estimating this is 0, because this makes f of x equal to 0. Now, there's a lot behind this, and I'm kind of going pretty quickly. But this is the general idea. We want to find the minimizer of the loss function. So how do we do that? Well, essentially, it's what we just said. And I'm going to, in the interest of time, just skip quite quickly. So we'll say when the usual, okay, let me just say what mean squared error is. So we have this idea of mean squared error, MSE, mean squared error. So you can think of this as what we did with residual sum of squares, but we just take the mean. Now, what is the mean in this case? So we have a linear model. That's the model that the learning algorithm is going to find. So if we want to minimize well, hang on, maybe I should just write what MSE actually is. So we want to minimize MSE. So this is our loss function. So we can think of it as, I'll write it with an uppercase L just to make it clear, because we've got two parameters, A and B, right? So we've got a loss function of two parameters, A and B. Those are the only two parameters. We want to find the A and B that are minimizers in this sense, that they make the loss function as small as possible, 0 ideally. So MSE, so we want to minimize MSE. Well, what is MSE? So MSE is 1 over n sum I is 1 to n, goes from 1 to n. Now what do we have? Well, we have data, right? That's all we know. We know that we want to fit a linear regression, and we have data. So the data is in pairs yi, xi. But the loss function is defined in terms of y and y hat. So y hat is, so we have yi in the data, and we have y hat, which is this thing here. So let me, I might just rub this out, actually. Give me more space. So the minimizer is, the MSE is going to be yi, which is an actual value in the data, and then y hat. But we know that y hat is a plus b x. And for a particular piece of data, we have xi. Okay, so we're plugging xi into the function, and yi is the actual value, and we want to minimize this difference. Sorry, I forgot to put the square in. So this part is the residual. Actually, this part is the residual sum of squares that we had before. And MSE, the mean squared error, is just we take the mean. So the strategy is to, and I'm definitely not going to have time to get through all of this, is to take the derivatives. My bad. Yeah, you're right. You're quite right. Yeah. Thank you. Oops. Okay, so the strategy is to take derivatives and set to 0. So you've probably seen this kind of thing before. Okay, so we've got we have two parameters. We could have done this just for simple linear regression, but we'll do it for the two parameters. We've got A and B. So for each one, we need to find an expression which is the minimization, the optimization. So if we take derivatives of these two things, we need to take the partial derivative of each one individually. So let's do it for A. So d of the loss function, big L, dA. Okay, so chain rule, because we've got, well, let's just look at this thing. So we've got 1 over n, and then this expands into a big sum, and then these things also are sums, but they're squared, right? So we have to do something with this. Well, the first part is reasonably straightforward. This is a big sum. The derivative goes inside, essentially. So I'll just skip to that. So we're going to end up with, or we're going to start with 1 over n. I might just, to save time, drop the full indexing. And then inside this, we have d dA, and then this expression, y minus a minus bxi squared. Okay, and then let's look at this. So we have got the sum, 1 over n, we got the sum. Okay, so this this square thing has got to come down, and then we have the expression. So just applying the chain rule. And then we have to differentiate this inner expression, dA. So yi minus a minus bxi. Okay, so we're differentiating with respect to a. Okay, so the only thing here that depends on a is a itself. So we end up with, I'll just go up here. What we end up with is 1 over n. Yeah, negative 1, that's right. Sum I. Well, it's I'll write it out in full just to make it clear that I haven't magically produced it from somewhere. Bxi, and then there's a negative 1. All right, so that is the end point of the finding the derivative. So what we have to do next is set this thing to 0. So I'll write it out here. 1 over n, sum I. Now let's see. I want to. I'll just write out the thing we had before. So 2 yi minus a minus bxi minus 1 equals 0. All right, so we can look at this, and the first thing we can observe is that we can get rid of the constants because this thing is set to 0. We can divide by 2 both sides, and that's not going to change the 0. So we can eliminate the constants. And then the second thing we can do is, and I'm going to sort of skip over a couple of steps because I'm going to run out of time otherwise. We can yeah, so I'll just 1 over n sum I. Keep an eye on what I'm doing because I'll probably make a typo. Yi. Just expanding this out, right? 1 over n, sum I. So the a can go there. and then minus 1 over n sum I bxi all equals 0. Now, A and B are actually not indexed, so they're not strictly part of the sum, so we can move them to here. This is indexed, so yi. So we can have A over n come outside the sum. Just for clarity, I'll put a 1 in here. And then the same with the b. We'll have b over n, and we'll say that's 1 xi, just to kind of make it clear, and that all equals 0. All right, now we can make an observation. We can say that this, well, what's this thing here? This is summing all the yi's and then dividing by n. Well, that's essentially the mean of the y's, the sample mean of the y's. So we can write that using, this is the notation that gets used, y bar. Now, this thing here is n times a over n, which is just a. And this thing here is b over n, sum 1 times xi. So 1 over n times sum xi is the mean of the x's, and the n's cancel to give us b. So it's b, and by the same reasoning, we get x bar, the average, the mean of the x's. Okay, and I'm just going to have to finish this because we're out of time, but we'll pick it up next time. And but what we want is an expression for a, right? Because we're doing this. Okay, so to get an expression for a, we can just rewrite this expression here as a equals y bar minus b x bar. Okay, so that gives us an expression